Okay, good morning. Did you guys do anything interesting over Labor Day? Yeah? What'd you do?
I went to Splash.
Splash. Where's that?
It's a nightclub.
Okay,
Corrections.
nice. Fun. All right, so last week we left off kind of talking big picture overview of sort of what a typical surface water drinking water treatment plant would look like. And just kind of grazed the surface here, just kind of named each of the components. And one of the things we'll find is several of these are applicable to both water and wastewater treatment. Should be a little bit obvious in that, it's a water treatment technology, therefore there's a lot of flexibility there for treating water, right? So first of all, sedimentation is going to be what we'll talk about first, and that is definitely used in both drinking and wastewater treatment. Correspondingly, we have a process, because if we look, we actually have sedimentation twice here. We have a process that can improve it for us. And so we're going to first introduce sedimentation, and then we're going to take a look at coagulation dosing and flocculation. Those two combined are the tools we use to make particles more sticky, which will make them larger, which will make them settle faster. So that's a reason we do it, and the reason we do it twice is because we can actually settle a lot just on the first go, and we don't have to waste our coagulant on all those particles that are already going to settle by going ahead and letting them settle, and then doing our coagulation. So that's where we're going to be today. We definitely use sedimentation for bacteria in a wastewater treatment plant. Once we let them grow up to such high numbers that they're forming these little particles and sticking together. So we'll definitely see this even in our wastewater treatment segment. So sedimentation is really just all about using gravity and then understanding the force balance between particles. And for the sake of our class, we're going to assume that rather than realistic particles that are going to be weird shaped and probably a variety of sizes, generally we're going to keep it simple and say, okay, well, let's imagine a case where we have perfectly spherical particles. They're all the same size. What's the math under that circumstance? I'll tell you a little bit about some of the alternate scenarios or maybe empirical tests in practice. How do we measure or predict sedimentation? But we can do some nice calculations if we do make these assumptions. So in terms of the nice calculation side of things, it's probably a good idea to start a reactor design, sedimentation basin design, on the basis of, hey, let's assume something about these particles. That way we know we'll have some control over at least this type of particle in our operation, and we can be confident of that control. Okay, so we assume they're spherical, we assume they're all the same size, then we can do a force balance on them, and we can say, well, the forces acting on our particles, we have the force of gravity pulling down, we have a buoyant force acting upwards, so that would be FB and FG. And then if we have motion, we're going to have a drag force acting in opposition of that direction. So we'll say, for the sake of this, we'll say that force of drag should be upwards, assuming our particles are falling. There is a bit of a special case where we might do particle flotation instead of sedimentation. Typically requires aerating the system with very fine bubbles, letting all the particles stick to bubbles, and then letting all of those bubble-laden particles float to the surface and do kind of reverse sedimentation. It's essentially using the same principles. We're using primarily the buoyant force there instead in that case. But mostly we'll look at this force balance where the force of gravity is dominant, or at least we hope so. the design criteria then would be to see, okay, well, how fast is that particle settling? How much time do I need to give it before the particles that are sitting at the top of the water column reach the floor, which means we can capture them and they'll stick to the floor, and then we'll scrape them out later. So that's ultimately the goal, is to find that terminal velocity. That's going to tell us, or we can use that to say how much time to reach bottom. Of whatever basin we're using. Okay, so we have then this force of gravity we can describe as mass times acceleration. This would be the mass of the particle, so mp times g, which is the acceleration due to gravity. We could rewrite that as, instead of just mass, we can put it in terms of other dimensions that we can actually more easily measure about the particle. So we can more easily understand something about the volume of the particle and the density of the particle based on more crude methods than taking one individual particle and putting it on a scale and weighing what change of mass happened when you did that, right? That's very difficult and not at all practical. So rather than measure the mass, we look for volume, because you could maybe separate a whole bunch with a filtration and say, okay, well, what volume is occupied there, or even better, we can use a very simple light scattering technique to get a good estimation based on how much they're wiggling. It's called a light scattering technique, and that gives us a diameter in real time without too many fancy things, just a little laser and a computer to do some estimations based on those observations. Then we get diameter, and that's why we can use that for volume. The density, likewise, we can measure in bulk, or even just do some sedimentation experimentation to figure it out, or make some assumptions just to say, well, we think it's approximately this, or we'd like to remove particles of such and such density. We could even start there. So those are kind of the innate properties of the particles. We can get some estimations here more easily than the mass, so we use that volume times density gives us mass times the acceleration due to gravity. All right, so we also have a similar setup for the mass of water displaced, because the mass of the water displaced is what gives us a buoyant force, right? It's that amount of water that would have been there that would be happy to fill in underneath that particle if that particle went away. Well, that's our buoyant force, right? So if you try to take a beach ball and dunk it underwater in a swimming pool, it's displacing a lot of water, and that's essentially that force you feel pulling up is the weight of water trying to get underneath it. It's that amount of water you're displacing, that's the mass, or the force acting upwards against that beach ball. So for the buoyant force, then, it's the mass of the water instead of the particle times the acceleration due to gravity, and we can get the mass of the water in the same manner by saying, okay, well, we have the volume of the particle, so it's still Vp here, times the density, but this time density of the water. Whereas the rho p here is density of the particle. I'll have all this written out on the next slide too, I believe. Okay, then we have the last thing is the force, the drag force, and that's going to be essentially a relationship with the surface area in contact as it's going by. So we have, it's also a function of how viscous the water is. So mu here is the dynamic viscosity. So we have 3 mu pi times the speed at which it's traveling. So just like skydiving, you'll reach a terminal velocity. This is actually that terminal velocity that we're looking for. So when we solve our equations, this is how we get it. I'll this is how we get the terminal velocity. And it's also, like I said, a function of the diameter. Okay, so force of drag, not going to go into the derivation of that particular equation, but let's just take that for granted that that is the appropriate drag force equation, and we can solve this then for the settling velocity, and that's what we can use to design our reactors. Okay, does that make some sense? All right, so have it all written out here, and the units that we need to use. So I mentioned mu, that's the dynamic viscosity of water. We have a lookup table for that based on temperature. So if it's hotter water tends to be a little less viscous than colder water. And so we have some relationship there. Doing particle sedimentation in the winter is actually a little bit different than in the summer, just based on that alone. We have that in units of kilograms per meter per second. So that's telling us, if we take a look at our units, we need to make sure everything's in meters and seconds. If you think about measuring a tiny, tiny little particle that we're trying to separate from our water in meters, it's like, well, here's a meter with this tiny, tiny little particle. So we have to make sure that, as we're doing our unit conversions, and we're dealing with cubic meters of water, there's going to be some very small fractions, right? It's times 10 to the minus 6 or whatever. Okay, but just so keep that in mind. And seconds, everything will be in seconds. So when we say how many meters per second is this particle falling, well, not many, right? Especially if we're doing kind of a slow process where we're expecting these particles to be settling over over some time and giving it plenty of time through our system. This will also be typically just something like 10 to the minus 4, 10 to the minus 5, something like that. It's typical values. Okay, we have acceleration due to gravity. Remember from physics, that's going to be 9.8, or if you want to be even more accurate, 9.81 meters per second squared. We've got the mass of either the water displaced or the particle here. That'll be kilograms. We have the volume of the particle in cubic meters. So again, this volume term is going to be very, very few cubic meters for one of these tiny little particles, but we're going to keep it in meters. And we've got density of particles, kilograms per cubic meter, and density of water. And the density of water is also going to be temperature dependent. Okay, so we already took a look at that table and said, hey, look, at 5 degrees Celsius, we have 1,000 grams per liter, right? 1 kilogram per liter. Okay, so then let's do this force balance. Essentially, we want to know, if you're skydiving, you could do, really, there's not much of a buoyant force. So in skydiving, the amount of air you're displacing is pretty small compared to the amount that weighs. So we can kind of ignore the buoyant force for skydiving, and then it's just force of gravity versus force of drag. But it's really the same calculation. We just have the buoyant force here as well. So if we do this, this calculation and solve for Vs, that's kind of the derivation I want to go through right now so that we have a nice equation for Vs. So we can set this up. I'm going to go ahead and write out in the terms on the right here. So we'll say force of gravity, volume of the particle, times the rho of the particle, times acceleration due to gravity is equal to the buoyant force, so volume of particle, times the density of the water, times acceleration due to gravity, plus this drag term, 3 mu times pi times the velocity, settling velocity that we're looking for, times the diameter of the particle. Okay, so we've got some particle diameters, particle volumes. We'll probably convert everything into just diameters in a moment, but first, let's just go ahead and get the velocity term by itself. So we'll say Vs times 3 mu pi dp is going to be equal to volume of that particle times rho p times g minus volume of the particle rho times g. Okay, on the right side we see perhaps some convenient factoring out here with the volume of the particle twice and the g twice. We'll simplify that a little bit. And so we'll go ahead and divide. We'll simplify and divide here. So I'm going to divide both sides by 3 mu pi and dp. But first, as I'm writing it out, I'll say this is going to be volume of the particle times g. I'm going to go ahead and factor those out. And so we have inside the density of the particle minus the density of the water. All that divided by the other stuff. Before I write that out, one thing we'll notice here is essentially that settling velocity is a function of the difference between the density of the particle and the density of the water. So that difference is key, and we see it clearly right here now, which is kind of gives us some confirmation. And if you do forget exactly, I mean, you'll actually have this on your equation sheet, but just to think about it, as you're going, it's that difference that drives your speed, right? It's the difference between how heavy the particle is or how dense it is compared to the density of the water. That's really driving most of it. Okay, so on the bottom then we have 3 mu pi and dp. Okay, so let's just take one little tangent here and say the volume of a sphere, in this case our particle, is going to be equal to what function of diameter? Anybody remember? We can start with r if you'd like. I think it's, anybody have it? Should be, I think, 3 pi r cubed over 4. Is that correct? Yeah. Okay. So then to convert from r to diameter, so r cubed is equal to diameter over 2 cubed. So that's going to be r cubed is equal to diameter over 8, right? Did I do that right? 2 cubed is 8?
I think it's 4/3 instead of
4/3. Okay. Yeah, I was thinking in my mind, something's not quite right. Yeah, thank you. 4/3 pi r cubed. Okay. So then we can put in this d over 8 instead of d cubed over 8 instead of r here. So if we put this volume of a sphere, we can say, we'll just say 4, and I'm sorry about the writing on top of these skydivers here, 4 pi r cubed divided by 3 times 8 is 24. So it's 1 over 6 essentially. We'll just say pi r cubed over 6. Diameter, sorry. Converted to diameter. Okay. So with that, instead of the VP up here, we can insert that function and say pi. I'll go ahead and put it on the top and the bottom here. I'll put pi and 6 on the bottom, pi on top, 6 on the bottom, dp cubed. All of that's our v term right there. Just putting it in there, and then I'll multiply everything else across. Times g times rho particle minus rho divided by the remainder here, which was 3 times pi times dp. Okay, so then we can do some simplification and get a nice, neat equation for our Vs. So with that, we'll say Vs here is equal to, the pi's are going to cancel, the dp's will cancel to an extent, so this will become 2 here. So it'll be, I'll just write it out how the book has it. It'll be force of gravity times that difference in density times dp squared, all that divided by 18. Okay? And that's possible because we assumed we had a perfect sphere for particles. Any questions?
What happened to the mu?
The mu's should have canceled. Oh, sorry. Mu should not have canceled. Mu should be right here. Thank you. The pi's canceled. Mu, I just forgot to write. And which makes sense. It still should be a function of the viscosity of the water. If you were trying to settle particles through honey, you could kind of just visualize that's not really going to work very well. Huh? That will take many years. Okay, so that's a nice equation. We will use that. And remember, the units are going to be important here. So if we do take a look at the units, we've got meters per second squared. We've got densities, which is going to be mass per volume. So that'll be kilograms per cubic meters, which means we're going to have our diameter, these really small particles, in meters. Okay, so it'll have to be meters, kilograms per cubic meters, meters and seconds. All of those divided by this 18 mu. So mu is in kilograms per meter per second. So again, meters and seconds everywhere, kilograms. All of those will eventually simplify to meters per second units. Good way to check the process as well. Okay, so now that we have some conception of how to assume or define a sedimentation velocity, how do we put it then into practice? Well, turns out that there's a couple different reactor designs that are very common. In drinking water treatment, we typically call this a sedimentation basin or possibly a clarifier. Clarifier is more often probably used in wastewater treatment. But a sedimentation basin, clarifier, whatever we're talking about, we can do it in several forms. And essentially what we want to do is we want to look at, if this is a height on this y-axis, if this is height, so we're looking at a cross-section, we want to have a particle, any particle in the system, be completely settled. That's sort of our design criteria. And that means if we have flow going through from left to right, and we'll just call this length here, then by the time the water flowing through the system is going to reach the end, because really we don't want to ever do this in a batch system, right? We don't want to fill it, let it settle, and then drain it, and then fill it again, right? That would be pretty wasteful. So we want a flow-through system. And so essentially what we want is by the time water reaches the end here, we have to make the particle hit the bottom in order to be separated, because that way it sticks to the bottom. Whatever flow, usually we harvest water kind of from the upper area, but the flow of water still does have to go this way, right? So the water flowing through, if the particle doesn't hit the bottom before it hits, before we've reached the end of what we've defined as a reactor, it's not necessarily settled. So just thinking of water flowing straight through for a moment, if it hits the bottom before it leaves, then we're good. So then essentially our design has to get us right there to the corner to make sure that it will settle. Any particle that happened to be lower in the water column will follow the same trajectory and will definitely settle before, right? So if we can settle that one, we are confident that they will all settle. Now, if we happen to have a smaller particle that's going even slower, that one is probably not going to settle, right? So it's based on that speed at which it's going downwards. That's the, I guess the vector we could say is that settling velocity that's going to determine that aspect. So we could look at this line in terms of the speed of the flow and the speed of the sedimentation velocity. Okay, so those are kind of the two things we need to balance. And we have two different types of systems that can operate this way, as you see here pictured. We have these rectangular basins, which, at first glance looks exactly like what we have here, except that I took a cross-section view as if we were inside it swimming and looking, flat across it like that. This is the picture I drew. And so really that's just one little slice that's, maybe a few meters deep. And we're just thinking about it like looking into it that way. The other one would be a circular system. And in this case, it's not, maybe not immediately obvious, but you can actually do the same thing if you just take flow coming from the inside. So I'll draw this, I guess, up here. So flow is going to be going radially outward from the centerpiece and collected along the edges. And then if you have that type of a system, you can take a cross section just from that centerpiece to the edge, and you can draw a perfect rectangle from that center point off to the edge. So we're just taking one radius essentially and taking it vertically upwards. And so we're making a rectangular cross-sectional area that's going to give us the exact same type of rectangle here from a circular system. Okay, so that simplifies our math, because again, it just comes down to, all right, well, very, very simple physics of how long does it take for the particle to reach the end, and does it hit the bottom first? Okay, does that make sense? Great. And so one thing to consider here, and the area of the floor itself is going to be important. If we think about in 3 dimensions here, kind of what the rest of the area looks like for a rectangular basin, obviously this would be the basin area. So we'll say area of the basin. You know what, let's do this. Call that length and width. The area of the basin would be equal to length times width. That would be the case for this, for a rectangular one. For a circular one, obviously this part would change a bit. And so if we were considering this system, then in that case we would have a circular system where all that area under this one, that would be the area of a circle, right? Pi r squared. So area basin for that one would be pi r squared. Okay, but otherwise the same principle applies in terms of how long you have to travel. It's just that area of the basin could change. Okay, so let's put this into some math then. So again, we're going to assume spherical particles. Spherical and identical. then we can draw the system where we have the height of a particle up here, or let's say we're going to define the height of the particle that we're interested in as the highest one in the system, because that is so if this is our total height, h, then the height of the particle really is, we're going to set to be that in order to define a system that's going to remove all of our particles, which is, more succinctly said right here. For complete removal, HP is going to be equal to h. So in that case, we're going to design our system based on that. We'll say our height of the particle, we want to be equal to that sedimentation velocity times our hydraulic retention time. So remember that theta is V over Q. We can get a volume if we have some dimensions, right? We have a length, probably some width. And a height. So we could have some idea of our flow rate and our system. And what we want is to find a critical settling velocity. So we want V naught, some equation for V naught, to know that, okay, given that particle that starts at the top, it has to reach the bottom before they leave. What's that equation for V naught? Okay, so let's take a moment to define or derive that then. So if we're saying the height of the particle, that the height that the particle needs to fall in that right amount of time is the settling velocity times the amount of time the water is in there. Okay, the water's in there for some amount of time. That's kind of the obvious, okay, is it going to hit the bottom yet? So we're going to rewrite that and just say the height is equal to Vs times theta. This is a settling velocity. I'm going to try to do kind of a squigglier V for the velocity terms because it's a lowercase. We're going to have uppercase V for volume here. So I'll try to keep that separate for you. So if that's our equation, we can actually do something interesting because the height is also a defining term of the volume, right? The height of this reactor is important for the volume of the reactor as well. So rather than leave it as theta, I'm going to go ahead and say that's the settling velocity times V over Q. And thinking about the volume, well, that's where our height is going to come from. So what we'll say is this is going to be the height of the reactor times the area of the basin. And that's one way we can keep the rectangular versus circular systems essentially the same in terms of math, at least in terms of this equation, because the area of the basin is either length times width or the area of the circle, right? So we can just leave it as AB here and then figure it out as needed. So this is going to be height times area of the basin divided by Q. We still have the Vs here. So height is equal to the volume, the settling velocity times the height. So let's solve this for settling velocity. So we have a new equation for settling velocity here. And that's going to be Vs is equal to essentially the height divided by the height divided by the area and times Q. So this is going to be equal to Q over AB. Okay, and like we said a minute ago, when we're defining the sedimentation velocity as the critical sedimentation velocity, when we say that particular particle is the speed at which it's going to be the one particle that can be removed. Anything slower is not removed. We're calling that the critical one. Anything slower than this velocity here will never be removed from a system like this, because it's not going to reach the bottom. So when we have that, that's when we said H is equal to HP, and so we can write V naught is equal to Q over AB. So really, I probably should have just said V naught the whole time here, but I think the point should be clear. And I believe I'm giving you this on your equation sheet. Double check that, but I think it's there. And one thing that's really interesting to note here is because the volume related to height, and height was really the key thing for our particle to fall. That was kind of how we defined it. The height of the reactor actually became not important at all, which is kind of funny. So you think that, okay, the particle has to fall some height, and so surely the particle height, the height of the reactor is really important. Well, it turns out it doesn't actually depend on that at all. What matters, in a way it matters, right? So what matters is the flow rate through that area. And your flow rate itself, if you tried to have the same system and you had a really small height, your flow rate would increase if nothing else changed, right? So your height will affect your flow rate in that sense. And if you think about it, one of the largest sedimentation basins around is the Gulf of Mexico, in a sense, right? So the Mississippi flows out, and the Mississippi Delta fans out really, really wide, and it's not, it's not super deep, but the amount of water flowing, it spreads quite a bit, and then that ends up giving it plenty of room to handle that amount of flow. Right, so if you were to imagine dumping that in a very much deeper or much shallower system, your flow rate would change, or you can think about how the dynamics, maybe the natural system would widen even further or whatever. You can really think about all of that in terms of what flow rate is going over what area. Okay, so when we're solving these problems, we need that area of the basin, we need the flow rate, and that's going to give us that critical design velocity, and we can compare a particular particle against our design velocity, or we could design a system for a particular particle. Okay, so just to make that a little bit more explicit here, again, our VS case is the one where they're all settling, or excuse me, V naught case, that's the particular one where they all settle across that spot. If we have different sedimentation velocities, we'll say VS1 and a VS2. They're not necessarily there. So if the VS1 here, the downward component is larger than the downward component of V naught, so VS1 is greater than V naught. Therefore, all particles are removed. So even the least likely one that started up at the top was for sure removed, right? Whereas this VS2 is smaller than V naught. We'll say not all removed. But what's interesting is you can see that some of them probably are. In fact, this VS2, we see that it dropped some amount, some portion of the height, it did fall. So we could just simply by basic geometry, we can actually take that same height here and say, okay, anything in those, if we draw the same exact velocity, any of those in there should have settled. Okay? Does that make sense? So we're just I'll just write this as some difference that we notice. Should be the same difference right there. And so that portion should settle. Which means, as we'll see on the next slide, we should be able to define that as a proportionality for these rectangular systems and say, okay, well, if the settling velocity is some proportion of the critical settling velocity, then proportionally we should have that percentage removed. Okay, does that make sense? Because this is all assuming we have nice laminar flow, nothing weird, turbulent happening, and a particle is going to settle at a constant velocity, because we're assuming, again, we reach that terminal settling velocity. Okay, so here I think I just was going to derive that a little further. In fact, let's see what I've got. Okay. All right, so we could define P as a percentage of particle removal. Of particles removed. And you know what? I'm sorry, I'm going to skip forward just for a second because I think I have a slide with a bit more detail on it. Yeah, okay. So I think I just added an extra slide here. Didn't really need it. Covered all this. So we'll leave this alone and we'll come back to this concept in just a moment. Okay, so I talked about earlier already, but just to be a little extra clear, if we have a rectangular basin, sorry, this would be looking down on it now. So this, we'd have coming up instead, up and out of the page, so to speak. We'd have a length, width, and height in this case. Our area of the basin, of course, is length times width. And in this case, the area of the basin would be pi r squared, or if we were dealing with a diameter, we could do pi diameter squared over 4. Okay. And this would be a top-down view. Okay. All right, so there are a couple of interesting things we can do with sedimentation. One would be to increase the rate at which we can sediment things by simply making it shallower artificially. So this would be called a high rate settler. It requires just a little bit more infrastructure than like a swimming pool. So you could kind of use a swimming pool just about. Flowing water through. And we can do that by adding these shelves, because essentially, instead of just having the area of the basin, let's say here, well, we could simply add shelves along the way. Doesn't take up a whole lot of volume in the reactor, but any particles that are moving through and hit the edge here will settle. They'll be settled. Since they got stuck, those should stop. And we'll usually incline them a little bit to encourage that, and to encourage them to slide away from the collection point as they accumulate. So it's kind of a neat little trick. Depending on the flow rates and things, maybe it's not practical for all systems, but it certainly is a way to increase your surface area and multiply it, in this case probably about 4 times as much surface area. That means you can either operate at a higher flow rate or use simply a smaller sedimentation basin. Okay, it probably comes with a few more mechanical challenges in terms of how to clean these shelves properly without just kicking up the sediment into the water column again. And all that, which may be a little easier if you just have the one spot at the bottom. But they are used sometimes, and it is pretty neat. This portion is not quite. Well, let's talk about that. So in this case, if you do have I guess a V naught would then, instead of be for the entire chamber, it would be more like from here to here, right? And so if you're not removing a particular particle in that space, this part is not true. I'm sorry, this was accidentally repeated for something. But that proportion is much tighter, so it's harder to just get some fraction of them because you just don't have as much space. Okay, here's where I meant to have this part. So, pardon my my error there. One other interesting design is called an upflow reactor, or upflow sedimentation basin, and it's kind of weird because we have a system where we're going to flow water from the bottom upwards. So this is the flow. And so as the water is moving upwards, whereas the circular systems we've dealt with in the past, the water is flowing from the middle but outwards. In this case, it's flowing literally upwards and being harvested over the edge here. Well, what's really interesting is if we make it kind of trapezoidal like this and wider as we go upwards, well, the velocity of the water, I'll say VW, and I'll put initial here, and the velocity of the water up here, I'll say final, I guess, for F. It's going to slow down because there's more and more space for the water to occupy, and so it's slowing down as it nears the top. And it turns out that the sedimentation velocity downwards needs to be essentially just barely over this V upwards, the flow of the water upwards, in order for us to have sedimentation. So we'll call this one, the V final up here, V naught, because that's our critical sedimentation velocity. We have to at least meet that. The particles have to be falling at least as fast as the water is moving upwards to reach a 0 point, and then maybe they'll hit some other particles and settle faster or something. But generally, anything faster than that will ultimately settle downwards, and at least will not escape over that edge. So we can say V naught is greater than that velocity down here, that velocity of the water initially. Don't worry about the math or the symbols here. I'm just writing it just to say it, right? This velocity is faster than up here, and then so anytime the critical velocity is slower than the Vs, we have 100% removal. Otherwise, we get 0% removal because the particles are just taken over the edge. Okay, so it's kind of an odd system. Maybe it makes sense with particular types of particles if they're very sticky naturally and are going to stick together or something and make kind of a little blanket of particles at some level because they're fast enough to go downwards to that point and then they're going to catch. Maybe there's some interesting systems where that makes a lot of sense, but it's not very typical. Just a little bit of a tangent, another way we could use sedimentation. I imagine that a flotation system would be a little bit similar, and perhaps this would be a good way to apply a flotation system, but you would be collecting the stuff at the top and maybe have a different way to direct the rest of the flow. Okay, so coming back to our case, I wanted to elaborate on this with the P, and I realized, as I thought, I did have a slide dedicated to it. So I drew a couple lines like this earlier, and I said, well, what happens when our design velocity would be here, V naught, but what happens if we're slower, right? I measured some distance here to here. You could also potentially measure, and what you'll notice is if we take a look at the different distances here, given the geometry. If we call this A and this B, this would also be A and this would also be B, right? That was kind of the entire point there. So with that, and I'll just leave that there. With that, we can say our VS, in this case, this one would be VS, this one would also be VS. When we compare the two, it really is a ratio, and we can say that P, the percentage of particles removed, is VS over V naught times 100%. So pretty straightforward there. And if we think about it, if everything else in the system is the same, but the VS is changing, the only thing that changes is the height at which they fell, right? So since we'll go ahead and say since system is constant, changes in VS are changes in height settled, or height traveled, I guess. Because we have the same amount of time in the system, have all that the same, it's just going to drop some proportion. So P as VS over V critical times 100%. We could use this to find, maybe if we were given a percentage, we could then find, well, what's the actual sedimentation velocity, given that we know something about the design. Or we could find the design, or we could find the P. You know, we can use this to solve different aspects of a sedimentation reactor. Okay, and this, by the way, we are assuming that VS is lower, right? So if V naught is greater than VS, because we can't have more than 100% particles removed, so P is always less than or equal to 100%, right? If you find you're solving this and you found you've removed 150%, think back and realize that, oh, I must have reversed these two, right? Or there must be a similar error somewhere. So we never need to use this if the settling velocity of a particular particle is faster than the design velocity. Okay, so keep those concepts distinct, right? It's a design. V naught is design, and VS is some random Joe particle. Maybe that's the one we designed for, but a particle. Of some sort. You know, it's just whatever particle we happen to be talking about. Does that make sense? Okay. All right, so here I have some practice for you. I have a Kahoot as well, so give this your attention and we'll do a Kahoot in a couple minutes. I'll read it through with you and kind of walk you through any big picture questions you have. And then it'll be an exercise. You guys can work together if you want, but get your own answers is what I'll ask, because I'll have you answer those in a minute. So this is a silt removal in a clarifier. Example 6.1 from our book. It says a drinking water treatment plant uses a circular sedimentation basin to treat 3 million gallons per day of river water. Explains MGD and gives a conversion for you there. See appendix A. All right. After a storm occurs upstream, the river often carries 0.1 millimeter silt particles with an average density of 2.2 grams per centimeter cubed. The silt must be removed before the water can be used. The plant's clarifier is 3.5 meters deep and 21 meters in diameter. water is 15 degrees C. So part A, what is the hydraulic detention time of the clarifier? And part B, will the clarifier remove all the particles in the river water? I think I've got the parameters here. Let me just check real quick. Okay. I will get those written up here for you in a moment. You're going to need mu, of course, and the density of the water. So I'll get those for you in a moment. But okay, so coming back to the question B, what will the clarifier remove all of the particles from the river water? So essentially, we're looking for theta, and we're looking for is Vs greater than V naught. Okay. So go ahead and start working on that. I'll get this portion written up, and then we'll work through it together in a few minutes. All right, I'm actually going to go ahead and just edit my PowerPoint real quick. Don't mind me. Oops. Be just a moment. Okay. Sorry. Be back in a moment. So I had a question from online a couple minutes ago about what time should you convert to, and I was just double checking my Kahoot just now because I realized that. Well, first of all, you obviously have to do seconds for a lot of your calculations, but my options are in seconds and in hours. So make sure that for part A, make sure to have whichever one's most reasonable. Or you'll have a minute to convert if you need to. But
It's like I could totally look at it, but I was like, that's it's deep. Because this one's like, yeah, but I'm looking at it. Oh, I took one. I think, I used to play too. Why did you get 100%? I did your way and I got 192. I got 36,900. That's the way I got it. That's a lot.
I said, how far have you guys gotten? You
I'm trying to figure out.
almost done with the A and B, or just okay?
That's what I did the first time, and then when we take these other, I don't think you're. No, I think you're right. Okay, the 21. So I used the view sphere, this formula, and I got theta to be 36 hours. Yeah. And then I used the IRH whatever, and I got it to be 91. It's just talking about the clarifier, so you could use the 21 for the diameter. I think you're right. Because I could it doesn't want to make me feel better about it. Like, I didn't think what you did, I just did this. Okay. We'll stick with it. This is simple.
All right. Use your 8-9 number when signing in. All right. Anybody else need a moment?
Yeah, I'm sorry. I forgot my number. Oh, no.
Okay. All right. So I'm gonna let you go ahead and answer, but I know I didn't give you quite enough time for the problem, and it's also kind of funny to just jump into like we talked about it and then here's like the full problem.
I didn't because though.
Is it up here? Anybody? It's the game pen is right here. It's 651-086.
Thank you.
Mm-hmm.
Hours.
So you'll just for participating, you'll get most, if not all, credit. Okay. So no, don't fear there, and we'll work through the answers next time to walk you through it. Oh. Okay, so the answer was 2.6 hours. Okay. All right, so if you got to part B, let's hear it. If not, just guess it, based on what your feeling is, yeah. And then I have one last question after this, so if you're already done with this one. Think about what do you think, would sedimentation work well or not on the Death Star or on a space station? All right, I'm going to go ahead and skip here because I think everybody's answered. The right answer was, by the way, no, they did not full settle. Okay, last question. Okay, space station. I forgot what it was. And sorry about that for those online. I know I skipped that. Don't worry about it. Okay, and the best answer for that is no, there's not much gravity there. All right, so we'll see you next time. We'll talk more about it. And I know, don't worry about the grades on this one.